Hi, and welcome everyone to the Calibrating Analytical Instruments webinar. We appreciate you joining us today. My name is Katie Turner. I will be one of your hosts. I am Marketing Manager with BMEX, and I am joined today by two other hosts, Sarah Kinnan, BMEX Client Services Manager, and Michaela Cooper with ISA. I want to, again, welcome you all. There are probably over 500 of you here right now from over 70 countries throughout the world. And I am coming to you actually live from BMEX's corporate headquarters in Pietarsaari, Finland. Just to let you know the layout of today's webinar, we are utilizing video in this webinar, so you should be able to see our faces. There will be two question-answer sessions, one about halfway through and one at the end. Please type your questions into the question box. You can type those in at any point, and we will get to as many as we possibly can. There will also be live polls. We do encourage you to participate. When the presenter puts up a poll, simply click on your answer, and they will read through the results at the end. Finally, we will have a survey at the end of the webinar. We have been doing a series of educational webinars along with ISA for several years now, and our content and topics are always based on what you tell us, so we do appreciate the feedback that we get for what you guys want to see next. And with that, I'll hand it over to Sarah to introduce our speakers for today.
Thanks, Katie. Joining us today, we have Ian Verhappen, Senior Project Manager at SEMA Plus, a certified automation professional, certified specialist in analytical technology, and professional engineer in several Canadian provinces with 30+ years experience in the automation industry, including 25 years in plant support role and a site process analyzer specialist. Ian is also a certified instructor, contributor to ISA's Process Analyzer Handbook, as well as LIPTAC's Instrument Engineering Handbook, and columnist for several trade journals. He is also actively involved in the development of global automation standards, including those related to the process analysis for ISA and the IEC representing Canada on a number of committees. As Technical Director, Ned Espy has promoted calibration management with BMEX for 20+ years. Ned has developed best practices for calibration with a focus on pressure, temperature, and multivariable instruments. He is a consistent editorial contributor to the leading industry publications and has received significant recognition within the automation industry. Today, Ned teaches calibration best practices and provides technical support to the end users and the BMEX team in North America. Last but not least, we have Roy Tomolino, who has been teaching calibration management for 15 years. Throughout his career, he's taught on 4 different continents to people from over 40 different countries. His previous roles include technical marketing engineer and worldwide trainer for Hewlett-Packard, as well as application engineer with Honeywell. Today, Roy is a trainer and calibration evangelist to all of North America. Thank you for joining us today, gentlemen, and Katie, back to you.
Thank you, Sarah. Before I hand it over to our subject matter experts for today, I'd like to officially announce a Best Calibration Practices interactive workshop that will be held on August 2nd and 3rd at Harvard University. If you're interested in joining this one-of-a-kind event, you can visit resources.bmex.com/interactive-calibration-workshop-2017. I know that's a mouthful, so don't worry about jotting it down too quickly. I will be sending a link to everyone following the webinar. Basically, it's a 2-day event all about calibration, all technical, all educational, includes a tour of Harvard's Blackstone steam plant, and if you do attend, you get 11 professional development hours. And with that, I'd like to hand it over to Ian to start the presentation for today. Thank you.
Well, hello, and thank you for that wonderful introduction, Sarah and Katie. And as you see here, here's today's session, we'll be covering two different single-point calibration technologies. Firstly, pH, and the second will be point gas detectors. And these are both very common technologies that we all use. And as always, if there's questions, we do have the Q&A session. So without further ado, we'll get started with just some basic theory related to pH. I think all of us are probably familiar with the traditional pH curve, and really what we're illustrating here in this diagram are two items. One, that it's a logarithmic relationship, which means that a very small change in pH can give us a large change in output, and also that we have the equivalence point, which is known as pH 7, which is basically the mid-scale, and we set that as our reference. So all of us, I know, because we're engineers, technicians, love mathematics. And so here are the two equations that we need to know, or at least be cognizant of when we're working with pH. The equation on the left is the Sorensen or pH equation, which illustrates the log relationship, and on the right is the Nernst equation. And so the reason we're showing the Nernst equation on the right is that you can see we have two factors that we need to consider. The slope, right, which is of the pH curve, and so the slope is, as you can see with that RT, the temperature dependence factor, is something that we need to really watch, and has a big impact. We'll illustrate that later. And then the other is that we have an offset, so we showed that in the previous slide, of pH 7 at 0 millivolts. But you recognize that the far right hand of the equation, the log H3O plus, which shows that pH is a function of the hydrogen ion concentration, is again the right hand side of is just the pH equation again. So how does the pH electrode itself work? And you can see here on the left we have a cutaway of the pH electrode. And so what we're measuring is the potential, the difference between the charges on the inside and the outside of this glass membrane. And on the glass membrane we have a gel layer, which is typically about 1,000 angstroms, and so not very thick, and therefore easily damaged or sheared off. And you can see that the glass itself is made of a combination of lithium and silicon-based compound. So the electrode works where we have a constant concentration of hydrogen ions in the inside, and then on the outside, which is where we're measuring, that hydrogen ion concentration is going to change. So obviously, if we have more or a positive charge on the outside of the membrane, hydrogen is going to, the charges, not the ions themselves, will migrate in, and that's an acidic solution. Whereas if the hydrogen concentration is lower on the outside, then we would have a negative charge, and we would measure that as an alkaline solution. So if we're doing this measurement, right, we need to have a reference electrode. And so in a very high sensitivity, they have separate reference electrodes. And basically the electrode is not responsive to the concentration in the solution, but we have to create that difference, or the reference point. So the reference electrode is made of pH that is not sensitive to the hydrogen ions, and for that reason, right, it's a half cell where we have a constant junction gradually leaking or weeping out the electrolyte, which is why we have to have a refill to replenish the electrolyte. So effectively we are creating a small cell, right, between the reference electrode and the actual pH measurement electrode. And so that's the measurement system as we see here, right? We have the indicator electrode on the left where we have the voltage across that measuring membrane, and then we have the saturated solution with which is the reference on the right, and then we measure the voltage between the two electrodes, and of course the hydrogen ions in our sample under test are what complete the conductive element in the liquid. Okay, but because this is cumbersome and expensive to have multiple electrodes, we typically on a commercial system use something called a combination electrode, which we show on the next slide. So here's the combination electrode. You can see that we have all the elements. We have the refill opening, we have the reference junction going down the right, and then we have the inner buffer and the glass membrane down at the very bottom. Now the shape of that membrane can be a wide range of shapes depending on what you're trying to measure, and in some cases it's actually can almost be like a spear for measuring the pH of semi-solids, so that it's made to be more durable like that. But generally, when the thing we need to do, like any of our instruments or equipment, we always have to maintain it. So our pH electrodes, when we're not using them, we generally need to store them wet, right? We're maintaining that gel layer. And so typically what we do is we store it in a pH 4 buffer solution, and do not put it in deionized water or alkaline buffers. So obviously deionized water means that there's no ions, so what you're going to do is all the hydrogen that's inside, right, in that buffer, that would be high charge, so it would all want to leak out, right? If your buffer or if your sensor does dry out, generally just putting it in some pH 4 buffer overnight tends to re-equilibrate it and get it ready to be put into service. So it's not the end of the world if your buffer dries out. Here is that Nernst equation at work. So you can see that the slope changes as a function of temperature, and so what typically your sample, we always condition or try to condition our sample system for a pH system so that it's constant. Now if you're putting your pH probe directly into the process, then of course you can do temperature compensation. And so if you have a temperature compensated pH electrode, effectively what you're doing is moving up and down the slope line, the slope that we see here, the solid black line. However, if we have a difference in temperature when we calibrate, what you'll see is that the slope will change and then we'll be on the dashed line, and so then we would be calibrating and measuring on two different curves, which will introduce error into our measurement. And so it's just some other troubleshooting things beside the measurement that you see here. Just for summary, if your readings are off, it's almost always check your meter, your cable, and your electrode is the typical things. Remember, we have an electrical circuit, so we just need to check the different pieces of the circuit to make sure that they're all working properly. And so the cause on the right is very common, but some of the symptoms that you can see is poor response, offset, slope, calibration error, and drifting, right? So just keep these things in mind. And of course, we have to clean things. You know, everybody thinks, oh, it's just a tissue or a Kim wipe. Generally, even though we think that's really soft, paper tissue can damage the glass. You know, so some of these glasses are quite sensitive. As a minimum, they will remove that gel layer, so then it will take some time to reestablish that layer, and potentially you can get you know, the static, and that can cause a surge, right? When you get a static charge, we've all been the shock. And then if the junction itself, it gets blocked, most typically that's our reference junction, then you can clean it in an ultrasonic bath. Again, notice that it's not a pure solution, that we have a small acidic concentration in that ultrasonic bath. So rather than, as we see here, rather than you know, the different ways to clean it, so if we have a silver sulfide electrode, basically again we're using a hydrochloric acid. If it's silver chloride, then you just use ammonia. So now we're using, instead of an acid, we're going to use a base to clean it. And if it's with proteins, because we do measure like agar or these types of things, as we know, cultures are very sensitive to pH, then we would need to again use a slight acid solution for cleaning that electrode. And then the buffers themselves. So here are the most commonly used buffers. We have a buffer of 4, 7, 10, and 12. The molarity is shown, and how many grams of the chemical needs to be put into the water to create that. But on the far right, you can see the temperature sensitivity going from 0 degrees, which is basically freezing. 25 degrees is the typical reference point, reference temperature for pH measurement, or 40 degrees, which means a nice warm summer day, which would be probably not quite right, but it would be just over 100 degrees Fahrenheit. And you can see that for pH 4, that difference is probably not too much, but for pH 7, which is supposed to be the equal point, right, we can get that logarithmic change starts to show itself, and the same as we go to the higher pHs, that exhibits itself even a bit higher. And so that's the end of the theory. I'm sure you'll have some more questions, but we get to start by asking you a question first. So if everyone can just tick the one, we'll watch the results, give you a minute or two for that, and then have a quick chat on what it means. Okay, wow. So it's kind of all over the place, and but pretty evenly split between an order of magnitude difference, 0.1 to +1 pH as the two ends. And of course, being logarithmic, that's even more dramatic. But the 0.1 pH relevant just shows how accurate, or how a small change can actually be measured with the sensitivity of these electrodes. Thanks for all that good stuff, everyone. And we'll now move over to Ned.
All right, thank you, Ian. That was great, very informative, and looks like on my graph here, I used a tolerance of 0.3, so maybe I had a pretty good average for what our audience said, but obviously if it was 0.1, this guy would fail. If it was ±1 pH, this blue area here, this would be looking really, really good. And buffer solutions, I've learned, are typically better than 0.02, but as Ian alluded to, temperature can cause a pretty significant swing. So you need to be when you're doing calibration, you do need to be aware of any temperature differences in the solution versus the process. But when we talk about calibration, one thing about pH probes and the associated transmitters is, they may drift, they may go a little high, get a little low or whatever, but during testing, they really have good repeatability and no hysteresis. So you don't need to do an up-down test. Really checking it at a low and a high, low, medium, and high, whichever, it's going to give you the same results. Also, Ian mentioned cleaning. Obviously, you might want to do an as found prior to cleaning, and then after you do your cleaning procedure, and you can make adjustments and then demonstrate an as left change for all that work. We see with our customers, most people are doing a 2 or 3 point calibration, sort of a low, medium, high approach. So on this graph, we're showing 4, 7, and 10, which really are, I guess, are the most common testing that we see out there. But you need to pick test points that fit your application, your process, and certainly you can get by with a 2 point check that's around your normal operating process pH. So on the next slide, we have some procedural information, and I'm not going to go through every one of these, but we thought it would be good to leave you with this information where you can maybe incorporate some of these ideas into your procedure. The second bullet there is mentioning this temperature probe. Again, make sure that you address temperature correction when you're doing calibration. And then over on the right, at the top there, it says visually inspect electrode and reference ports. That's always good practice to see if there might be something that you do need to clean or correct. And as you're moving through the buffer solutions, you're going to see Roy rinse the probe off with distilled water. So that's also good practice. So I think that's just a little bit of insight on tips for calibration, but now Roy gets to show you how to do it.
All right, thank you, Ned. Let me just share my screen here. All right, and one more step. There we go. I am a professional. Do not attempt what I'm about to do on your own without proper supervision. That's why I have Ned here. Well, technically, he's not right here. Let me grab my camera. I need everybody to grab onto your desk or your chair. Hold on one second. So let's show you what we've got going here. We have different fluids here for different pH solutions. We've got a calibrator to measure our transmitter. We have a pH transmitter. This happens to be a Rosemont Model 56. This also does conductivity too, but we're not taking advantage of that piece of this. And I've got a pH fluid here. I've got my probe in my little stand that I made in about, I don't know, 10-15 minutes using reclaimed wood and parts. And I'm going to hang my webcam off of this clamp that you see. Here's my rinsing station. We've got water to wash off, and I've got a water dip here. And then we have different pH fluid as well. And you notice somehow I got into the authorized area, and nobody knows I'm in here. So the different fluid, I've got one of them. And so back again, my assistant thought it would be funny if the fluid was out on the desk and I didn't know what was what. Apparently nothing is labeled here. So I need to pick out the proper one. So scientifically, there's a way to do this. If you didn't know which was which, or what was your pH buffer solution, what would you do? How could you know? We've got this. We've got a couple. Whoa. You know, this one could be a couple different things, and I'm not sure. Well. Okay, luckily that was an energy drink. That one's okay. This is some kind of sports drink. I don't know. This one. Okay, I don't think that's it, but all right, that tastes like flat beer. That can't be right. And so we've got these, the final two. Okay, that's it. This is my pH 10, the missing one. I'm gonna put that over here. This is gonna take me a minute. So I need to bring up my calibration software, so hopefully everybody can see my screen right now. I have this analyzer, AIT24. I've got two different tests for it, and one of them is simply just an analyzer, and then the other one is a transmitter, a pH transmitter. And I actually want to refire this up again. Just hit the letter A, so AIT24. Now I'll send this over to the calibrator, so I'm sending it now. There's my two functions, sending, and I already had them on there, but I'm going to overwrite them anyway, so that's done. Next thing I'll do is bring up my calibrator. So the calibrator itself, if I go to documenting calibrator, that's where our tests are. And the very top one, if you weren't using a transmitter and you were just calibrating a temperature probe, or not temperature, a pH probe rather, it would look like this. Look on the screen now, you can see that you're keying in a value. You know that your initial pH is going to be some qualification, it's qualified, can you see that? So this is for pH, and it's color-coded. You know what, I could have just looked at these bottles. I wouldn't have had to taste them all. So that's pH 4. And then the output could be an analog, actually it'd be a digital readout of something that's showing you what it is, and you'd key that in as well. But let me back out of here. We're not doing that. We have a transmitter that's doing part of this work for us. So with the transmitter, we will input what pH we're showing, and then we'll measure the current. So this one, the range of pH is 0 to 14. And the range of current is 4 to 20. I'm not providing loop power because this thing is already being powered. So let me start this up. And let me hit start. And you're going for a ride again. Hold on. Let me get that cable out of the way. So you're looking at my pH transmitter right now. So we're showing 3.98 pH. Now it's supposed to be 4. My tolerance on this pH happens to be 0.02. So it's within that uncertainty level. And we're also showing 8.55 milliamps on the transmitter. And you can see on my calibrator, we're actually showing 8.4843. So we're measuring what that thing is giving us. So on the calibrator, we actually need to put in what we're seeing on the screen, 3.98. So I'm going to click on the calibrator. This is the keyed in portion, 3.98. And we're measuring the output. Our error is 0.05 pH. So let me accept this point. The next one is our 10 pH. And now that we know what our 10 is, we know which vial, boy, and it was vial. So here's my 10 pH I'm going to put in here. And unfortunately, I don't have a way to show you guys what I'm doing here, but I'm going to lift out this probe and I'll put it into the water, and then I'll rinse it out. Should have Ned give us some feedback here while we're doing this. So I'm just swapping these out right here. So I just need to rinse out that probe, and I've got my 10 pH solution in here. Good, rinsing, rinsing, rinsing. And here we go. Now, it's in the 10 pH, so you can see the pH on our transmitter increasing. Now, I timed this. It needs a good solid minute in order to stabilize, and actually even more than that, 3 to 5 minutes. Ian will know the actual proper time that you should let this thing rest or stabilize. But from the perspective of performing this calibration, I'm going to give it an ample amount of time, just a little bit over a minute anyway, and I'm not going to wait as long as I would if this were a proper calibration. And you can see on the picture, we have 15 point something milliamps, and we're reading a little bit low on the calibrator side. So that means that the transmitter itself could be trimmed. So we're up to 9.8586. And while that's working, let me again show. So there was some really nice stand that came with this probe, but apparently it didn't make it into the box, so I had to make my own. So I appreciate your patience on this. So this is the setup. This is the calibrator right next to it. You are seeing a live screenshot of the calibrator, but I just wanted you to know that that's not an emulator. You're seeing live on the screen what's going on. The tolerance that I picked out for this test is 0.1 pH. And right now we're sitting at 9.9. And again, there's my station. Let me hang this up here again. So we're at 9.9. If I go into the calibrator and pick 9.9 is what we're seeing into it. Given this current that we're actually measuring, we are getting about 0.05, 0.04 pH error. And I'm just going to take this right now. Well, you saw that we just changed 9.91. And if I waited another 5 minutes or longer, it would continue to climb up to 10 pH as what my testing has shown. But for the sake of time, we're not going to allow that. So let me accept this point. So we passed. Our maximum error was 0.05 pH. If I wanted to, I could put a note here, but here's the graph itself. I only tested it at 4 and I tested it at 10. Here's our raw numbers. And here's some other questions you can put in here, but I'm not going to answer that one. Let me save this thing as found. Now our results are here. Let me just disconnect this guy and then bring up the software itself. So I need to unload this test. Calibration, receive. I want to confirm external references because I was using a pH standard that the software or the calibrator didn't know about. So I'll bring this one over and receive it. And before, let me do this here. I know you guys are thinking, please put it back on the screen. I know, but I'm back. Before I did this test, I put in these buffer solutions in the software as a calibrator. Now this is where I connect those dots and say I used this buffer solution for number 4 of this lot number, etc. So the repeats, let me go to as found 1, and point number 1 was my pH standard, which is down here, pH, and I used this one with this serial number, or this was the lot number off the bottle. Now for point number 2, I'm still using this pH standard, but I used this pH 10 solution with this lot number. And now I'll hit OK, and it brought it over. So now we'll find it. Right here is our test result. And let me just bring up a calibration certificate because that's the way that I would want to view this information. So I'll preview it. Let me zoom in here. So the certificate itself, this is all of our information, and this is what makes it traceable all the way up to the top, the national laboratories or the national standards. If I scroll down under calibrators, here's where I show my pH buffer solution, and I say refer to bottle. The different bottles are my 4 and my 10. And I've got the lot numbers, including due dates. When my due dates are essentially when the bottle says that it expires. And then the output is my MC6 calibrator, which was measuring the current on the output. So here we see our dots. The blue lines represent tolerance, and these guide bands that you're seeing is the uncertainty of my standard. On my pH bottles, it said that it was plus or minus 0.02 pH, that it was accurate to within 0.02. So I put that into my standard, and what you're seeing is a visual representation of that 0.02. It could be, if I'm 4, it could be anywhere from 3.98 up to 4.02. And that's what those bars mean. So that's uncertainty just on a visual perspective. Here's my numbers, and then who did it. So this is a complete calibration of a pH transmitter. We didn't need to do any trimming, but we could if we needed to. We could go in and do the trim on the pH side. We could also do the trim on the milliamp output side, and then run this again as an as left. So with that, let's take it to our first Q&A session.
Thank you, Roy. Gentlemen, if you will all join us here. Okay, your presentation has been pretty comprehensive so far because we don't have too many questions. So if you haven't already, join the discussion by submitting your question at any time using the Q&A box on the right-hand side of your screen. If we miss your question, we'll hold it until the final Q&A session, and if we miss it then, we will answer it later on using email. So let's jump right into the first question. Okay, so we have an attendee who's measuring pH in aeration basins and in general run between 6.25 to 6.50 pH. He says we use a 2-point calibration, 4 and 7 buffers. Would it be better to calibrate with 4 and 10 buffers instead of 4 and 7 buffers?
Well, it's Ian here. The other guys might have more to say, but generally I would just stay with where you are, the 4 and 7, because you want to, you're doing the right thing. You're spanning your expected measurement range. You're always going to stay acidic because then you go on the other side, right? So you're not going to change from an acid to an alkaline or vice versa. So you have the right range. And just because you're near the end, as we've seen, the response tends to be quite linear. So no, you're as far as I believe, you're doing everything right.
Yeah, I mean, and 2 points saves you time. I mean, instead of having to rinse a third time. So good practice.
What acid would you recommend using when cleaning a pH probe in a wastewater application?
Well, it depends on how, you don't want to say the word, the S word, the situation is, but obviously you would still use the rinse. If it gets clogged, the ultrasonic tends to be the best way to clean it, because wiping, as we indicated, tends to take off that protective gel layer, unless you wanted to go to more of a solid state pH, which we didn't talk about here. That could take a bit more abuse, but generally the manufacturer, if there is some other than ultrasonic cleaning or just a wash off, they would provide that option. They certainly have. Some have like a brush. You can get very soft brush that could be used rather than a wipe. Just like you have different toothbrushes, right? I'm one of these guys that has sensitive teeth, so I use the fine or extra fine toothbrush. They have brushes as well to clean pH probes if it's kind of really scummy stuff that you're having to get off there. But non-contact ultrasonic would be the first choice. Otherwise, I'd look at maybe these brushes that the manufacturers tend to provide.
Thank you, Ian. Roy, during your demo, one attendee wanted to verify that the pH transmitter is sending a milliamp signal to the calibrator.
So that is true, and I didn't actually point that out. There are a couple leads coming out of the transmitter going into my calibrator, and that's how I'm measuring the current. But that is true.
Can you explain how to calibrate the pH electrode using only acid and base without buffers?
Ian?
Yeah, well, I'm trying to think how you would do it. I mean, buffers are I mean, they're pretty common. I mean, you can buy them at. I gave the equation that you could make them yourself, right? Mind you, with all the controls on chemicals now, maybe it's not as easy as when we had chemistry kits when we were younger. I mean, the only way to do it, if you had something that bracketed, like you're saying, with an acid and a base that bracketed pH 7, is you would have to have a traceable pH electrode that you would measure, right? And you know that so the would only be there's a minimum factor of 3 times accuracy, right? So whatever measurement you're making of your acid and your pH on either side, that pH electrode would have to be 3 times as sensitive as the one you're needing to use for your control. Now, the thing that's kind of a saving grace if you're out is that, remember, for control, it's not always the accuracy that's most important, but the repeatability. So as long as you're consistently wrong, so instead of being 7, that it's consistently 7.2, you can put that offset into your control system and still control at 7. But if you're using an acid and a base, it's just the rules of calibration. And Ned and Roy can verify that it's got to be a minimum of 3. Some people say 4 times the repeatability of the measurement system.
Yeah, you're right on, Ian. I don't know, Ian, could they use something portable, like they could insert it into the process and see if they're in the ballpark? That I wouldn't trim or adjust anything, but
yeah, well, I'm not sure if they're. I mean, I use that to calibrate density meters that I couldn't take out of service. I mean, yeah, you could use another electrode in your process, but then your big assumption is that your process doesn't change, right? That it's steady state while you're doing the electrode swapping around thing, right? So
maybe at the end, we are going to present our email addresses. Maybe that the person that asked that question could give us some more detail behind their question, and we'd be happy to take a look at it post presentation here.
Okay. All right, next question. How do we know that the time response of the pH electrode is correct?
Well, this is more of a controls question, right? We saw that when Roy was doing the calibration, that we quickly saw it escalate, and it's always an asymptotic approach, at least for most measurements. And typically, the manufacturer will tell you what the response time is for the probe. And one nice thing about using the calibrator is you can see that when you've reached sort of that equilibrium state. Roy, does the software have anything in there that can help these people with that question?
Well, there is you can put in delays, but there's also a feature in the calibrator which will detect if it's still ramping up or ramping down if it's not stable. So there's an indicator on there, but I think that's just a matter of looking at it. And when I stopped it, and let me actually bring this over, this thing has actually stayed pretty close now. It just dropped from 9.91 back to 9.90. And that's just observing it, I think, is the best. Once it stops climbing, or if it goes down a certain amount and then it goes back up the same amount, then you know that it's stable. And here's actually how, back to that previous question, this is the output of this transmitter, this gray wire. And I'm following it all the way back up. I've got bare wire connectors onto the top of the calibrator. So this is how I'm measuring current out of that transmitter.
Yeah, so the response time will be in every manufacturer's data sheet. So it will be on the data sheet for the product when you're buying it, what the expected response time is. Often shown as a T90, so 90% of the response.
Well, and with the calibrator, you could even test one manufacturer against another. If you have both available, you could put them in one pH buffer solution, move it to another one, and time it yourself, see which one has better response or whatever property you're looking for.
Yeah.
We are just about out of time, so we'll ask one more question, then hold the rest for later. They're pouring in. So, as far as good practice goes, what time do you allow for a probe to settle?
I think it's trial and error. I think you saw with Roy. Roy just made a good point. I guess, Roy, you had to do a little shuffle there for what, 60 seconds, no more than 2 minutes, and
yeah,
it moved from 4 to 10, and it stabilized at the 9.9. So at least a minute.
Yeah, I was going to say roughly a couple of minutes probably is reasonable. Most cases you should get pretty close in 2 minutes.
The one thing that was interesting.
Some people say 5, but sorry, Roy.
That's not a bad thing. One thing that I found interesting in my testing with this is going from a lower pH up to a higher was a lot faster, and I'm sure that this had to do with the first session that you talked about. But if I go from 10 down to 4, it wasn't just a minute or two, it was a good 10 minutes to get down to where it needed to be and then finally stabilize. So is it common to always go from a lower to a higher pH number? Is there a standard on that?
Yeah, normally you start at the bottom and go up, just for that reason that you said. It takes a lot longer to reverse, and I think it's just the shock of it, right?
Alrighty, I think that's it for our first section. Let's get back to the presentation. We did have one person ask for a specific thing during your demonstration, Roy, and maybe you can cover this now, or maybe you can cover it with them later. They wanted you to show them how to key in the standard pH to the calibrator. So if you can include that in your later demo, if not, you can talk about it later. But
go
ahead.
Ned's actually going to do something very similar in the second half. So
yeah, I'll mention it. I'll mention when you would key a number in. I'll do that.
Perfect.
Maybe remind me, Roy, if I forget.
Sure thing.
Alrighty, Katie, let's go back to you.
Thank you, Sarah. Thank you, guys. Before we hand it over to Ian to continue on with the presentation, I'd like to let you know about a calibration blog, Calibration Insights. It's blog.bmex.com, where you can find monthly articles all about calibration. One of our most popular ones so far this year is Calibration Uncertainty for Dummies, and there was recently an article about data integrity for all of you in the pharmaceutical industry. So definitely check that out. If you do subscribe to the blog, you'll get notifications every time a new blog post is posted. All right, take it away, Ian.
Okay, well, thanks again, Katie. And we start off with a question. And the reason is that because we're talking about we need to talk about fire and LEL, which is what we'll be talking about here with our gas detectors. We have the question. All of you should know this one because you breathe in and out. What is the level of oxygen in the atmosphere? ta-da, 67. Oh, someone must have it inverted almost there. So, but good stuff. Yes, it's 21%. Then nitrogen, of course, is the lion's share. So that's an important thing to remember for a number of different processes, including the operation of gas detectors, as we'll talk about shortly. So, excellent. Okay, so let's start looking at different types of detector technologies. One here is MOSFET or solid state. These aren't all that common, but generally the way it works is that in this case we're using as an example combustible gas, which is probably one of the most common gas detectors, combustible or LEL, lower explosive limit detector. And basically the gas consumes oxygen, which releases the electrons in the tin dioxide, going to the aluminum substrate, and then we get a current going through the dioxide, and we have a heater because we need to maintain a constant temperature here. The current, of course, is then proportional to the electrons released, and hence the data concentration. Some of the things to remember especially thanks for the question on response time, is that depending on your configuration, these detectors can take 20 to 90 seconds to respond, and they are best suited to relatively low humidities because they can only handle up to about 10% humidity. So there's something to just keep your eyes on. Then we have, these are becoming more common, are infrared gas detectors. And infrared can come in two shapes. The one on the bottom, where you have an infrared source and then a detector. And so the gas would permeate through the little holes here in the path length, and then we would measure the concentration of gas in over that short distance. The more common configuration is the double beam on the top. So you'll have a retroreflector or a mirror at the bottom of your gas detector, and then you'll have a light source and the IR source, and the typically two detectors tuned for specific wavelengths on also all the electronics. The advantage of the other one is all the electronics are on one side, plus you get twice as long a path length to make your measurement. And so the things to remember, or the most important thing to remember with any kind of spectrometer, is you have to find the right wavelength. And especially in the infrared, water kind of floods out a big section of the IR bands. So the bottom there is water, and so if we picked the wavelength for methane, so we have methane as the gas we're trying to measure, because that's the most common component. So natural gas that you get to your house or whatever is typically 97+% methane. So then the fuel gas in your plant is also typically methane. So the most common gas that we measure with a combustible gas detector is methane. And so you can see that if we use the wavelength up around kind of the 1300 there, that would overlap with water. And so, the previous slide we showed the two wavelengths. So you would have the reference wavelength would typically be where the yellow bar is, because you can see there both water and methane have very limited response in that wavelength. So that would be kind of around 2500 or something. And then we would actually calibrate our gas detector to be at about the 3000 point here for methane, because we have a nice big methane response, and it's relatively flat for water there. So that's typically why we do the the dual wavelength. Dual wavelength will also help us detect if we have dirty mirrors, these types of things as well. So infrared is quite specific, and that's why it's starting to become more popular. This one should look familiar to all of you. This is the electrochemical cell. A little bit like pH, right? There's our sensing electrode, our electrolyte, and our reference electrode. And typically we'll have a hydrophobic membrane just to protect it from water. And then we have a diffusion barrier where the gas comes through. Some alternate names for electrochemical are amperomeric or microfuel cell. And of course, the thing with electrochemical is we can, by picking the right combination of electrodes and electrolytes, we can select the gas that we want to measure. So electrochemical are not only used for LEL, but they're always also used for things like H2S, SO2, ammonia, specific gases. And so the resistor across the electrodes give us a current proportional to the gas concentration. Response time here is typically about 50 seconds. Relative humidity up to 95% on condensing. And one of the challenges, though, is partly because of the change in humidity and things like that, is that you can get drift being as high as 2% a month. So therefore, you have to calibrate a little more regularly. And then the catalytic or pellister. This is the Wheatstone bridge that all of us have probably known since high school. Basically what happens is we have an active bead which has a catalyst on it to encourage the, I'll put in quotes, burning of the gas at a temperature lower than, of course, we would actually get a flame. Though that temperature is still pretty high, it's around 400 to 600 degrees C. And what happens, as we know, with any time that the temperature changes, we change resistance. And so this changing resistance unbalances the Wheatstone bridge. So we have an uncoated reference bead that compensates for changes in ambient temperature. And then we have the catalyzed bead. So we're just measuring on those two sides. Nice fast response time on these, 10 to 15 seconds. Repeatability is pretty good, and they drift about 5 to 10% per year. And that's just part of the challenges with a catalytic, right? Largely because the catalyst could be contaminated. So I did mention about gas specificity and the need for how methane is the most common gas. The reason I mentioned this is because we typically calibrate for methane, but if it's likely that you're having hydrogen or propane or some other gas as the predominant gas in your facility that you're measuring for, you either have to calibrate for that gas, or you'll have to make a correction factor to adjust basically for the heating value. So this table here just shows some of the, how different it could be, right? So for the 100% methane is, so 60% propane is the equivalent to 100% methane reading. And the other thing, of course, that's important is having, because these are point detectors, is having the detector in the right place. So as we know, every gas has a different density relative to air, and so air has got a molecular weight of approximately 28. And, a lot of times you will get the specific gravity for gas, SG. It's relative to air, which is 1. So obviously if your number is less than 1, right, then it will rise. If it's higher than 1, then it will sink. So if your gas is heavier than air, you typically mount your detectors. So heavier than air would be like a H2S, hydrogen sulfide detector. It would be 6 to 12 inches above grade. and you always put a filter on for your every gas detector will have a little filter type thing, keeping spiders, dust, pollen out of the getting to that membrane, or in the case of IR, to the path. And typically you'll have also, that cover will be a splash guard, especially for the ones at grade, because there's rain and people hosing and washing down the plant, that kind of stuff. Generally, if it's lighter than air, which most LEL detectors are, they'd be higher up. They'd be either above the point source or up at near the peak of the building, which then means you'd have to run your calibration gas up there to calibrate them. And then the other thing we always look at is where would it leak? So flanges, that type of thing, and wind direction, right? So if your wind predominantly comes from the north, then you're going to want to place your gas detector slightly south of the leak point. Okay, so just some things to really be aware of. Almost all gas detectors are sensitive to silicone, sulfides, chloride, halogenated carbide, hydrocarbons. And so basically this is why we do not normally install our gas detectors until construction is completed, because guys are putting silicone seals around the building, all that kind of stuff, and you do so, you poison your sensor. Okay. And so avoid contamination. Just be aware of these things when you're working. And if all of a sudden your thing goes wonky, it might just be because someone was doing some work nearby and just, I'll just put a dab of silicone, and it got near got into your detector, right, and gave a false reading. As we've shown, right, all of these detectors, because they're based on a chemical reaction of one form or another, we pretty much all need oxygen. And so if your oxygen is too low, then your detector will not work. So a gas detector typically will not work in a nitrogen atmosphere. Okay. And we are using, as I said earlier, be a catalytic bead unit for this demonstration. The Crocon unit that we have here, they recommend a calibration every 6 months. And as is the case with a lot of gas detectors, they have an analog output as well as configurable alarm contacts, so that you could directly wire to a local alarm or relay panel. So now, to see if you're all paying attention, we have some questions again. So, which type of gas detector is most common in your facility? See if we guessed right on our LEL detectors. So that's pretty much what I expected. I'm great to see that the infrared is picking right up, probably for the reasons that it is a little less sensitive to other conditions, lower maintenance because there's no moving parts, so to speak, and calibration might be a little bit less. There's probably more electrochemicals than you think, because all your little personal gas monitors, pretty much all of those are going to be electrochemical. So, but yes, your installed point detectors, that's great stuff. Thank you. Okay. And now we have another question. So when you do your measurement, do you normally do it as a percent of reading, percent of full scale, or some other reference? And if you're not sure, then share that with us as well. Wow, that was quick. So yeah, so just remember percent of reading, percent of full scale. Be aware of the difference, right? And so full scale, generally it will be, so that means if you have a 0 to 100%, 1% accuracy means you'll get no greater resolution than 1%. If it's percent reading and you're reading 10%, you have 1% accuracy, then you're down to 0.1%, right? An order of magnitude difference. So be aware of that when you're specifying and buying your instruments as well. So I think now I hand it over to Ned, who will talk a little bit about the calibration. Oh, sorry, wrong Ned. Roy,
Hey,
sorry about that.
no worries. Thank you, Ian. So for the next section, we have slides. So Katie, could you go ahead and show your screen? I think Ned's set up as a presenter. So while that's going on, the thing we have coming up for you next, thank you, is calibrating a gas detector that's also connected to a transmitter. So the picture you see on your screen is the actual bottle that Ned will be using. And it's interesting what all is included with this. And with gas detectors, they do drift, but pretty much they do have good repeatability and no hysteresis, so there's no reason to go up and back down again. That's the whole reason for going up and down is testing for hysteresis. So performing a 2-point calibration is good, dealing with 0 and then some level of span. If you are doing an oxygen sensor, you just need to be aware of that earlier poll question that we asked of what percentage of oxygen is in the atmosphere normally, and it's around 21%. So if you have an oxygen sensor and you've got nothing on it, you're going to read 21%, or you should. So that's why sometimes we'll take a bottle of nitrogen and shoot that at the sensor to give us a 0 on the oxygen. So make sure you pick a proper source or proper bottle to do what you're doing. So nitrogen is common for 0 gas or air. Right now we're testing for methane, so just ambient air will be just fine for that. So the bottle that Ned has, you can see it on your screen there. It's got a number of different characteristics, so you could utilize this for a number of different things. It has 15 parts per million hydrogen sulfide, 100 parts per million carbon monoxide, 2.5% or the 50% LEL, lower explosive limit on methane. It's 18% oxygen, and the remainder is nitrogen. So the first thing we'll do is we'll check the 0, and then we'll check a span. So I believe that Ned's going to just put it, not feed it anything specifically, just the air in his room there. So we'll grab the 0, and then we'll do the span where he'll put up the bottle, connect it to a manifold somehow using some kind of black magic, I'm sure. And it does take a little while for that to change and to stabilize. So we also want to give it a certain flow rate, like 0.5 liter per minute. And if that is good, then you're actually done with the calibration. But if you see that it's not passing or it's outside of your allowable tolerance, then after that, as that high span, then you'll do the correction and then perform the test again. Your 0 and then your span. So with no further ado, you are about to see my stunt double. You know him as Ned. Ned, take it from here and show us. I think it's impossible to actually calibrate something with a magnet, but I have this feeling you're going to show us how to do that.
Yeah, I am going to show you with a magnet, and I've never been a stunt double before, so I'm kind of excited.
Thank you.
Okay, well, I'm going to do kind of the same thing Roy did. Let me take you on a little tour here. So I've got to spin the camera around a little bit, and I do want to thank our friends at Crocon for making this equipment available to us. Really is going to, I think, be informative for you. So here on the table I have the detector you saw Ian show. I have it upside down, so this isn't a good way to mount it, but it makes it easy for me to be hands-free here. And then here's the sample bottle. So this has 50% LEL methane as our standard. So when I turn on the regulator here, I'll expose the sensor to 50%. And then here's my calibrator, and just like Roy mentioned, I've got you know, 2 leads here measuring the milliamps, and you can see the white cable sneaking around inside the transmitter. So I'm measuring the 4 to 20 with my calibrator. So now let me show you see, I've shown you my screen. I messed up here. Let me show the MC6 controller. And I'm not going to call it my software, but you saw Roy, you know, downloaded to the calibrator. So I'm just going to jump right into documenting calibrator here. And so when I click on this, I have a lot of instruments in my MC6, but here's AIT25, my gas detector transmitter. So that's what's on the table here. So I tap that folder. Here's a little reminder message. It's reminding me that I should wait at least 60 seconds for stabilization when I'm exposing the sensor to span gas. So that's kind of a helpful reminder. And then just like you saw with Roy, we're going to be keying in either 0 or, in this test, 50% for the bottle. And we'll be looking for 4 and 12 milliamps on the output. So the range of this transmitter is specified this way. And if it was an indicator, the earlier question, this lower part would say keyed. So if it was an indicator, or maybe we were doing a loop test into the control system, this would say keyed, and as you're exposing it to the air or to the methane bottle, you would key in what is the actual reading. So instead of saying 4 to 20, it would say 0 to 100% LEL here, and you would just key in the reading. So you can do documentation with a keyed input and a keyed output. But this test is set up for measuring the milliamps, and actually it's off here. It's barely passing. It's right at 2% of span, and there's my pass-fail. So here I am at ambient conditions, and I'm getting 4.27 milliamps. So let's go ahead and start this test. And I'll go ahead and accept this pair of readings. And now it's telling me to move to the mid-range here. So my target is 50, my expected output would be 12. So I'm going to go to my regulator here and open this guy up, and you'll see the milliamps start to move. And remember, it said I should wait 60 seconds. So so it's kind of good, you know, you can just kind of watch these numbers, and when this sort of slows down and stabilizes out, you know you're getting close. Here we are, we're finally on the graph. It's jumping along here on the graph. But now it's starting to slow down a little bit. But still moving, and I can smell a sulfur smell, by the way. So the gas is coming into this little cup and exhausting here into the room. But we're looking pretty stable. It's obviously rising a little bit, but you can now see that this rate is so slow we can't even really see it see this ball moving on the graph. So I'm going to go ahead and accept this test point. And I'm going to go ahead and save my bottle. I'm going to turn it off. And in fact, I want to go back to 0, so I'm going to remove the little cup here so that my sensor has a chance to get back to 0% quicker. But it did pass, although barely, and it's got my name in there. But there's the graph that we just saw. So we're going to actually do a calibration and trim this guy. So so it was halfway out at full scale and was all the way out at 0. So let's go ahead and save this test as the as found. And so now here we are sitting at, and this is kind of interesting, it's come in a little bit here. Maybe having that cap on there was messing it up. So the way this guy works, as Roy said, we use a magnet. So you can see there's this little device here. But Crocon designed this so that you can move the transmitter without taking off the cover and exposing the electronics to a potentially harmful or intrinsic rated area. So you don't have to come out with a hot work permit. So to enter calibration mode, I just put my magnet here on the glass, and I can see it's kind of blinking. I guess you can't see that, but I can make it. I can move it down. Well, it's looking really good now. I'm just going to leave that alone. So I'm going to hit menu again, and it's now in span mode. So now I'm going to hook this guy back up and turn my gas back on. And let's get it back up to range here. And let's see, I want to let's see, I'm going to key in that my LEL is 50%, so I'm just in a troubleshooting mode here. There we go. And we're getting back up about where we were before at 11.8 milliamps. So I need to run the milliamps up. So let's see if we put the magnet here. There, I made it jump too much. And I made it go back down. So that's pretty good. I'm sitting here at 50, and I'm getting about 12.04. So that looks real good. So let's turn this guy off again, and let's see what happens when we go back to 0. So I've done an adjustment. I didn't really adjust the 0. I just adjusted the span. But let's hit our little start button here and give this guy a minute to come back down, and see how close we get to 0 or 4 milliamps. And in fact, one of the things Roy talked about, there is a little symbol here on the calibrator. It's just an logarithm that we have, and it's informing you as the technician that this signal's moving. It's not stable. So the calibrator wants to see a nice steady signal, and now it's starting, as it gets slower on the change here, that symbol goes away. So the idea is you can take a recording when this signal is nice and stable. So it's still running down a little bit, but it's looking pretty good. We're pretty close to 4 milliamps. And this signal's getting close enough. So I'm going to go ahead, just for time, and record that reading. Then I'm going to connect my bottle back up and do one more span gas. So here we go. So hopefully we'll get the repeatability out of this guy, and we're going to have a near perfect calibration here for the as left. And So appreciate your patience here. This is a little tedious, but here we're coming in. We're getting closer. We're getting closer. Still have some noise on the signal, so we're looking for that to go away. And now we're perfect. Let's see if now it's starting to slow down. So it's still creeping a little bit, but it's really a slow amount. So so I think I did a pretty good job. What do you think of that? We'll hit let's hit accept on that, and we'll just jump right. Look at that, it's perfect. Let's hit the save button, and we'll save that as the as left, combine it with the previous results. And so then we can back out of this test. I can close it here, and I'm back to my list of 49 instruments, and I can see I've got a green check that I've done this. The testing on this guy is complete. I can go get one of my other tags on the list. So I'm going to close this little app, and let's show you CMX now. And I think you can see this. Hopefully you can see this. Somebody let me know if they can't. But here I am on the AIT25.
Ned, we can't see it at this point.
Thank you. Thank you, Sarah. Can you see it now?
We sure can.
All right. So we're going to pull this in very quickly. I forgot to turn off my sample bottle. I can smell it. So I just turned that off. So now we're going to receive. So we're going to interrogate the calibrator. And one of the things Roy said is, remember, we use this, we need to tell the software what our external references were. So this is a little bit different for BMX. So we're going to first connect to the MC6, and here's the AI25 with both an as found, as left. I'm going to leave the other stuff on there, and in fact I'm going to delete this off the calibrator after I receive it. So we're going to pull it in, and just like Roy did, I have to say, for my as found on test point 1, I used ambient air. So here's my air category or calibrator, and then I just note that it's my 0 sample. And then for the span on the as found, instead of air, here's my methane. And if I had multiple bottles, they would all show here. So here's my 50% LEL bottle and the lot number. And we have to do the same little routine for the as left. So for test point 1, I used, again, good old air. It's free. And then for test point 2, on the as left, I used the same methane bottle. So pretty straightforward. So when I hit OK, I've connected the dots, as Roy said, and I've brought in the test. So now here's today's date, and just as a final thing, let's do the same thing that, well, I guess you can see the graph. You can also see the uncertainty or error of my gas is kind of large compared to this type parameter that we've selected here. But if we print the certificate out, and I'm going to use this one, and let's blow this up where you can see it better. So here I'm measuring methane monitor in some kind of tank storage area. It's a Crocon FlamGuard Plus unit. The range is 0 to 100%. But here's my sample gas. I used air and methane. So air is obviously air. And then I had this lot number bottle for the methane. And then my milliamps was measured by the MC6. And there's the graph as found, and then here's the as left, sort of this perfect line here. And then if we go down here, there's the numbers that were recorded by the calibrator. So fully documented test on a sample using sample bottles is our calibrator rather than a traditional electrical calibrator. So I'm going to turn it over to Katie.
Thank you, Ned. We are running a little short on time today, so I'll quickly go through a couple resources that we have that are related to this webinar and hand it back over to Sarah so we can get as many questions as possible in. There are two books that we'd like to recommend. One is Analytical Instrumentation. It's 36 chapters, covers a full range, all about process analyzer technology, including sample systems, purchase, maintenance, and validation. It includes all forms of technology like physical properties, chromatography, spectrology, wet chemistry, and detectors. The second book you see on the screen is Ultimate Calibration, second edition. It's a 203-page book with 19 articles all about calibration. To get access to both of these, just be sure to check your email when we send the recording and these resources to you following the webinar. The second resource and final resource I'd like to mention today is ISA training. ISA does offer on-site training as well as training at their corporate headquarters in North Carolina, and you can visit isa.org/training to learn more about their offerings. And with that, I'll hand it back over to Sarah to begin the final question and answer session.
Thank you, Katie. Gentlemen, if you'll all join us one more time. We have a lot of great questions here. We're going to answer as many as possible. But if your question is not answered, we will provide you all of our presenters' emails later on, so you can email them directly. Starting off, we have multiple attendees who would like to know how many points to use when calibrating a pH sensor. Is it necessary to do a 2-point test after the standardizing 1 point? And is there a benefit of using 3-point calibration versus a 2-point calibration?
Well, as we indicated in the first question and answer, you just really need to do the 2-point calibration because you're just spanning, either side of your measurement range should be more than sufficient. If you're operating right around 7, then you can get by with just the single point, the pH 7 solution.
Thank you, Ian. So assuming that the process under observation is in a steady state, can we still use only acids and bases to calibrate the electrode? And how will the sensitivity and accuracy be compromised in the process?
Well, it's as we said, it's more about repeatability, right? I've done, and we've all done it, right? We live in the plant, and we have to make the big assumptions. Repeatability is key, and if we're able to consistently get a reference between, that acid or base that we're using and what we're measuring with our sensors, then that'll work, right?
Yeah, I think if you have a clean process, you don't have to maybe calibrate as often, but if you're having to clean and have a harsh environment, I think by documenting your testing, you're going to know when something's normal and when something's not normal. Like you say, Ian, you want repeatability. You want to guarantee that the information coming into your system is correct.
Okay. Now, I'm not sure if I understood this question correctly. Maybe you guys can help me. as the sensor is not an integral part of the transmitter, how can one handle sensor trimming function, the sensor trimming function, with different sensors?
Well, that's there are some manufacturers that have put some intelligence in the sensor to help address that exact problem. The other option is it's just the same as when you're working with a safety system, right? You have to calibrate from end to end. So you have to calibrate from the sensor through to, in our case, the output from the transmitter. And by doing so, you'll take into account any deviations in the connections and interconnecting cable.
Okay. Based on your experience, what would a reasonable calibration frequency be?
Well, if you want to be conservative, follow the manufacturer's recommendations. These gentlemen will tell you more. One of the benefits of documenting all of your calibration is that you can you'll have a historical proof that you are to say that I want to make it longer. I did just that. Recommended calibration period. You know, manufacturer's conservative. He wants to make sure that he doesn't get blamed if something goes wrong. We had documentation, and we went from 3 months to 5 months calibration frequency on some of our gas detectors, but we had the documentation to prove that the drift was sufficiently low that we could get away with that.
Yeah, I agree with that answer. You kind of want to start with a conservative interval, whether it's the manufacturer or just your paranoia, whatever that interval is. But once you do 2 or 3 tests, you should be able to predict, you know, what kind of drift you're seeing. I wrote a paper, I think you can find it on our website, but you want to make the distinction of systematic drift versus random noise. And a lot of times you're over testing and you're seeing things go up and down, and it's just sort of random error that it naturally occurs. But if you start seeing it here, then the next time you go out it's a little higher, the next time you go out it's a little higher, that's systematic error, and that's where you need to calibrate and bring it back to factory new condition by trimming.
Is it a better practice to wash the pH probe with buffer solution between the switch from buffer 7 to buffer 4?
No. Your best bet is to use water. Distilled water is typically what people use. You get a little squeegee bottle, just like Nalgene, right? So you can spray it on. Some people, yeah, there you go. Roy's waving the exact bottle that most people use.
Not this. This.
Okay.
Yeah, you don't want to contaminate, whatever you do, you don't want to contaminate your buffer solutions. You don't want to get some 4 mixed in with some 10 or whatever.
Does the flow of gas make any impact on calibration?
If it's too high, it's not good. If it's low, it just takes longer. But generally, it's usually the gas detectors aren't that sensitive to it. If you don't want to be too high, because then you're wasting gas, and you go too low, then you're just wasting time. So that's really what drives it. On the IR, yeah, on the infrared it can have a factor, but on the other technologies, not so much.
And these sample bottles, they have a proper regulator. It's really an on-off switch, so they're kind of set up for you at a proper volume.
Good. I was wondering if yours was.
Pardon?
Good. I was wondering if yours was set up with a regulator.
Yeah, it's not a regulator that, you know, as you turn it, it allows more in. It's an on-off kind of thing.
Okay.
So it's a set pressure. It's preset.
Yeah.
Okay, we just have about 2 minutes left, so let's try to hit 2 more questions. Do you find any difference in accuracy with liquid and powdered buffers? Are the powdered mixes that you would add to water close to their stated accuracy? And do you stir the probe in the buffer?
So I wouldn't use the probe as my stir stick, if that's the second half of the question. But yeah, you can lightly, just to make sure that everything's, because you can get stagnant right against there, right? And then to make it up, yeah, it's just all about how accurately you measure the, that's why we showed grams per decimeter cubed of water. So if you just follow the instructions, it should be certainly within the tolerances that the stored buffer. One of the things, if you have a pre-made buffer, keep the cover on, because oxygen can cause them to gradually decompose. So yeah, that's it. Keep them in the jug with the lid on. So
make sure you label your stuff properly.
Yeah. Yeah, so some people actually prefer to mix it up themselves each time, just so that it doesn't deteriorate because someone left it in the beaker for a week.
Yeah, and it's like following a recipe. It's really important that you do the exact same recipe every time. So maybe use the same, measurement scoop or whatever you're using. Make sure it's the same thing, and then you will get repeatable results for sure.
You can calibrate your scale. The calibration cyclone, right? Yeah.
Yeah, it's our next topic.
Well, let's keep thinking about next topics, because that's all the time we have for today. Thank you, gentlemen.
Thanks, everyone.
Yeah, real pleasure. Thank you, everybody. We really appreciate you being out there.
So many of you had questions that were not answered. You will see the presenter's contact information on this slide here, so please reach out to them with your question after the webinar, and they will respond to you. If you missed any portion of today's webinar, we will send you a link to the recorded version afterwards, including that survey that will ask you how we did, be honest, and let us know what you would like us to cover next time. So that concludes the webinar. We know your time is valuable, so we'll let you get back to it. Thank you for attending. We've had a wonderful time with you today, and we will see you again soon.